So if I'm just reading a graph, I can figure out at any point where I am. So at 5 seconds, I have a displacement of 5 meters. At 6, 7, 8 seconds, I have a displacement of 11 meters. But if I want to know the velocity, the slope at any given point represents the instantaneous velocity. So slope equals velocity. And there's two ways we can use this. We can use the instantaneous velocity, where we're saying that I want to know the velocity at 6 seconds here. And if I want to know the velocity at 6 seconds, I need to know the slope at that point. Well, the slope at that point is the slope of this line. So I don't need to use this point exactly when I'm calculating that, because this whole line has the same slope. So to get the slope of this line, I'm going to figure out my rise over my run. Well, I'm at 5 and I go up to 11, and then I am at 5 here and I go over to 8. So my rise ends up being, it's going up 6. And my run, 1, 2, 3, ends up being 3. So the slope of this line here is, my slope is equal to a rise of 6 over 3 equals 2. And so my slope there is a slope of 2. And that means that my velocity is also 2. And on the rise, it's a displacement in meters. And my time is on the x, so 2 meters per second. So according to this graph and according to the rules, the slope at any given point represents the instantaneous velocity. So because it's this point, I need the slope of the line at that point, and this whole line follows that same slope. So if I were to get the instantaneous velocity right here, it's on that same line, it would be that same slope. So it's going 2 meters per second from 5 seconds on until 6, 7, 8 seconds total. So 2 meters per second there. If I wanted to find the instantaneous velocity, I'm going to switch colors here at 10 seconds. Let's just say 10 seconds right here. So the instantaneous velocity, now I have a negative slope. It's this whole line, so I can use this whole line to figure it out. And in this situation, I'm up here at 11, so my rise, I'll go here, rise over run, my rise is actually negative. It starts at 11 and it goes down to 0. So my rise is negative 11 meters, and my run is from 8, 9, 10, 11, 12. Is 4 seconds, 4 seconds. And so when I take and I divide that out, 11 divided by 4 gives me 2.75, but it's negative. So negative 2.75 meters per second. It tells me I'm going in the opposite direction than what I was before. Both of these are instantaneous slopes. I'm looking at what's happening at a given point. The instantaneous velocity here is different from the instantaneous velocity here, is different from here, is different from here. If I wanted to find an average velocity, then I would take 2 points that I wanted to find the average in between. And those can be any 2 points, but it's going to be between those two that ends up being the average that we get. So let's just say I wanted to know my average velocity in the first 10 seconds. My instantaneous velocity is that it is going in the opposite direction. But my average velocity for the first 10 seconds is that I would go from here to here, and I would draw that line. So when I put that line in, I'm going to do it in brown here. I'm not sure if you can tell the difference, but that line, the slope of that line is my average velocity from 0 seconds to 10 seconds. So I need the slope of this line. Well, if I follow this over here, it's at positive 5. So the slope here It's a rise of 5 and a run of 10. My average velocity in this time is 5/10, so 1/2 or 0.5 meters per second. Now that's the average. That's overall from start to finish. How far did I go in the amount of time that I had? When we're talking about the displacement time graph, slopes are what's important. The area under the curve does not play into what we can do with that graph. When we're talking about a velocity and time graph, the slope is going to be equal to the acceleration. So when we're doing a graph like this, slope equals acceleration. And so if it's an instantaneous slope, we're saying at any moment, what is the acceleration? So right here, in this part here, the slope is 0. And so because the slope is 0, the acceleration is also 0. It's staying right at 6 meters per second, 6 meters per second. It's moving 6 meters per second, 6 meters per second, 6 meters per second, 6 meters per second, 6 meters per second. At 5 seconds, it starts increasing in the velocity. It's getting faster. So it's getting a little faster, a little faster, a little faster, a little faster. Because we have a positive slope, we have a positive acceleration. In this situation, we can look and calculate what that acceleration is by determining the slope of this line. So anywhere on this line, if we do rise over run, we can get it. So if we go, our rise goes right up here, 8, 10, 12. So our rise is 6. It's positive 6. And our run brings us out to 11 seconds. It is also 6. And so for this section here, our slope equals our rise over our run. And it's equal to our acceleration is equal to positive 6 meters per second for the velocity change. Velocity is measured in meters per second, divided by 6 seconds. And if we have meters per second divided by seconds, we get 1 meters per second squared. So our acceleration from 5 to 11 seconds is 1 meter per second squared. When we go from here, our rise is 2, 4, 6, 8 down. So our slope equals negative 8 meters per second. And then over our time of 1, 2, 3, 4 seconds. 4 seconds. So in this situation, when we're coming along this line here, our acceleration equals negative 2 meters per second squared. The slope is equal to the acceleration, and at that instant point, it is the instantaneous acceleration. If we want to get the average acceleration between 2 points, we can do that. We just have to draw the slope of the line between those 2 points overall. So let's say that we're looking at the acceleration from start to finish, from 0 to 20 seconds. It's pretty close. It goes up, it comes back down. There's nothing that's too crazy, but if we go from 0 seconds to 20 seconds, our rise in that situation is just down 2. So our slope equals negative 2 meters per second squared. At the end, it's going 2 meters per second squared less than it was at the beginning. It went up a little bit, it went down a little bit more, but from start to finish, it was going at 6 meters per second to start, and it ended at 4 meters per second. So it is a rise of negative 2, and then a run of 20 seconds. So negative 2 divided by 20 gives us negative 0.1 meters per second squared. So whether you're trying to find the instantaneous acceleration, it's the slope at a point. So the slope here is going up, the slope there is going down. And you can get those accelerations. The slope here is positive 1 meter per second squared. And the slope here is negative 2 meters per second squared. Or if you're trying to get the average acceleration, you'll take from between the 2 points. In this case, we use this point here at 0 seconds, so 0.6. At 20 seconds, it was at 24, so our rise was a negative 2, and that happened over 20 seconds on average. And so it has an overall acceleration, an average acceleration of negative 0.1 meters per second squared. Now, the other thing about this graph can give us the most information for what we generally will do, is that if we want to know how far we've gone, it's the area under the curve. So let's say I want to know how far I've gone at 11 seconds. So we'll use 11 seconds right here. That means that the area under here, I'm going to put it in as yellow. I'm thinking you might be able to see it. It means that at 11 seconds, I have to take this area here. Now, anytime you'll be asked to do this, it'll be on something that is it's geometric shapes that you should be able to get pretty straightforward. And in this situation, if I want to know from 0 seconds to 11 seconds how far I've traveled, I need to know how much has happened here. So I'm going to break this into two separate boxes. The first box is going to be a rectangle. I'm going to break it into what I've got here. I know that it is 6 up and it goes over 11. 11 seconds and 6 meters per second. I went for 11 seconds at least 6 meters per second. So when I take 6 times 11, I get 66 meters. But that's not all, because then here I'm also getting faster. So I need the volume, or I need the area of this triangle. So for this triangle, I'm going from 5 to 11. So I've got 6 here. I'm going from 6, 8, 10, 12. I've got 6 here. And the area of a triangle is 1/2 base times height. And so I can say 1/2, 6, times 6. So 6 times 6 is 36. Half of that is 18 meters. Because I'm taking velocity in meters per second and multiplying that times time in seconds, I end up with meters. So my total displacement in that time, I'm going to add these two up. 18 plus 66, if I add them up, I end up with 84 meters. So anytime you're trying to figure out how far you've gone, you're getting the area underneath the graph line down to the 0. So if I wanted to know how far I went in the last 5 seconds, I would take my last 5 seconds and find the area here. And I've got 5 seconds there, and I'm going at 4 meters per second. 4 times 5 is 20 meters. So whatever's happening underneath is how far you've gone. The last one that we look at is acceleration. And acceleration doesn't usually give us a whole lot because we'll keep in constant acceleration frame of references here. But in this situation, we have acceleration on the vertical axis and we have time on the horizontal axis. And so when we look at this graph, our acceleration is at 2 meters per second squared. And it says the slope at any given point represents the rate of change of acceleration. So the slope here is 0, so the acceleration isn't changing. Can you be in frames of reference that have a changing acceleration? Yes. Are we going to do that in here? No. You need to start getting into taking derivatives in order to figure out what you're dealing with there. So we have a flat line for our acceleration, and what that means is we have an increasing velocity. The slope of joining any 2 points on the graph is the average change in acceleration. Again, this is a flat line graph here. So it means we have an acceleration. In this case, it's 2 meters per second squared. But that acceleration holds constant. The area under the curve represents the change in velocity. That's the part that we can do something with here. Because if I wanted to know how much does the velocity change in the first 8 seconds, I would take the area under the line up until the first 8 seconds. So I know that I'm at 2 meters per second squared, and I can take this all the way down till 8 seconds. So if I wanted to know my change in velocity, how much faster am I going than I had been, I have the area under the curve, so I've got 2 times 8, so it's 16 meters per second. So wherever I started, whatever I was doing to start off with, 8 seconds later, I'm going 16 meters per second faster than I had been. The other thing about an acceleration graph is it can tie together what's happening in the other graphs, the one of velocity in time and the one of displacement in time. And so as we're looking at this, if we know that our acceleration is at 2 meters per second squared, it means every second the velocity is getting 2 meters per second faster. And let's say that it's starting at 0, 0. I'm starting from rest. 1 second later, I'm going 2 meters per second faster. Another second later, I'm going 2 more meters per second faster. Another second, 2 more, 2 more, 2 more. So when I get this, I have this linear graph, this linear slope that has a slope of 2 meters per second squared here. How did I get that slope? Because acceleration is that. So the slope here is the acceleration, or the acceleration drives the slope here, depending on which way you're going. The other thing is that because we know our acceleration is getting faster, and I'm going to do this one as a sketch, it means that every second it's getting farther at a quicker rate than it had been the second before. So what happens is we have a little bit, we're moving a little bit, we're moving faster, we're moving faster, we're moving faster, we're moving faster. So that as every second goes by, it goes farther than it had in the previous second. So it might go 1 meter per second here, and then 2 meters in this next second, and then 3 meters in this next second. And so this slope continues to increase along the way. Anytime you have these 3 graphs, if the acceleration is at a constant acceleration that's not 0, then your velocity will be a linear slope, and then your displacement graph will be an x squared relationship.